Well, hello everyone, and thanks Kyle and Jen for inviting me to speak at this mini symposium. I will talk about stability of clusters in the second order Kuramoto model. And this is joint work with Mathew Mizuhara. So this is our recent preprint, which we posted on arXiv about a month ago. And so I gratefully acknowledge the support by NSF. For those who haven't seen this model before, so I'm going to introduce it. It's a network of coupled oscillators. So these are phase oscillators. U takes values in the unit circle. So the dynamics of each oscillator is relatively simple. So it's described by second order ODE. So we have some damping and the torque, right? And then the oscillators are coupled through this Kuramoto-like coupling. So they are pairwise coupled through sine function. There is a possible lag alpha. K stands for the strength of coupling. And so there is possibly some non-trivial connectivity, which is here in the model is defined by the adjacency matrix, Aij. Okay, so this model can be viewed as a generalization of the famous Kuramoto model of coupled phase oscillators. On the other hand, it has applications on its own. And perhaps it's best known for its applications to power systems. So each oscillator can be interpreted as a generator. And so these systems of this kind were very successful in modeling power grids. So one interesting feature of this model is that it also generates a variety of clusters. And also, so the synchronization problem is also meaningful in the context of this model, like in the classical Kuramoto model. And so I'm going to argue that these problems are related. And so I want to sort of building on the ideas and techniques which were developed for the original Kuramoto model. So, so the main question which we want to study is the stability of clusters, which is a non-trivial problem. Okay, so it is instructive, in my opinion, to view this model as a generalization of the Kuramoto model. And so for this reason, I will review certain facts about the original Kuramoto model, which I will be using later. So the classical Kuramoto model, so it's a model of coupled phase oscillators. Omegas are intrinsic frequencies, and in the classical setting, they are taken from a random distribution with density G, right? So the coupling is the same as before, so it's pretty much the same. This model illustrates an interesting phenomenon. So it's the transition from incoherent or mixing dynamics to synchronization. So since the frequencies are random and different, for small values of K, the dynamics is, so one sees this mixing dynamics where the oscillators are distributed practically uniformly around the circle, unit circle. And so this behavior persists for some values of K, but then at some point one can notice that there is a gradual build up of coherence, which eventually leads to synchronization, right? So this is best seen using the Kuramoto's order parameter, which is a very convenient measure of coherence. So if one takes the modulus of this complex quantity, where right, so for small values of K, so we see order parameter around 0, which corresponds to mixing. And then there is a transition to values close to 1, which corresponds to synchronization. And so what's interesting is that one can identify a precise value at which this transition takes place. And relate this value to the distribution of frequencies. So in case of unimodal symmetric even function G, so the critical value of K is given by this very simple expression, right? Surprisingly simple. And so that's, yeah, so this is the onset of synchronization in the Kuramoto model. So to understand this in more analytic terms, so one needs to go to the continuum limit as n tends to infinity. And since both of these patterns, the mixing patterns and these partially synchronized states, which we see, they are stochastic patterns. So the correct language to describe this behavior is the probabilistic language. And so one talks about probability distributions of these phases in the limit as n tends to infinity. And so one can describe the evolution of these probability densities, rho, using the mean field equation, or it's also called Vlasov equation. So the vector field in the Vlasov equation here, so it's, so for the Kuramoto model, so it describes it captures the coupling and the distribution of frequencies. And so for this equation, one can identify a steady state solution, which corresponds to the mixing state. So this is 1 over 2 pi. And so Strogatz and Mirola in 90s noticed that the stability analysis of this solution explains the transition to synchronization in this model. So this critical value of K, so this is precisely the value of K where the mixing state loses stability. So the rigorous mathematical analysis of this problem and the bifurcation analysis, so it's a very non-trivial problem, and it was worked out rigorously relatively recently. So the first person who did this was Hayata Chiba. And so now we have other approaches, other methods to this problem. And so recently with Hayata, we analyzed the transition, so this bifurcation for the Kuramoto model on graphs, so which also, so it requires the graph limits, and it also depends on the eigenvalues of the kernel operators defined by the graph limits. But so overall, it's the same phenomenon. So for a certain positive value of K, one gets a pitchfork bifurcation leading to synchronization. And so now, after this brief review of the original model, so I will turn to the second order model. And so now we are using the same setting. So we are interested in the second order Kuramoto model, where the omegas, which in this model correspond to torques, but I will keep referring to them as intrinsic frequencies to sort of maintain this analogy with the original model. And so we are going to assume that these omegas are taken from the probability distribution with density G. Okay, so one, like I said, so this model has a very interesting ability to generate clusters. And so these are some of the numerical simulations which show these clusters. So in each simulations, G is uniform. So it's uniform density over a certain interval. And so in the top row, you see cluster generated in the model with all-to-all coupling. So the graph is complete. So you can see 2 cluster solution, 3, 4, and in our experiments, we saw clusters with, patterns with more clusters. So the experiments in the bottom row show the same for the model on Erdős-Rényi graphs. So here the probability of connections is 0.1. So these are fairly sparse graphs. And so we can also generate clusters in this model. And so you can notice that, so neither the probability distribution, so it's uniform, so for frequencies, nor the connectivity, sort of promotes clusters in any way. So it has no bias, but still it's not hard to find initial conditions which leads to this stable cluster configurations. So furthermore, it's not uncommon to see multi-stability. So one can find regions in the parameter space where 1, 2, 3, and 4 cluster solutions are stable, and actually more stable simultaneously. So it's an interesting problem, which sort of motivates our interest in understanding stability of clusters. So there has been some work in this direction done, and so the probably most relevant paper is by Bilic, Brister, and Bilic in 2016. But so they analyze model with which is deterministic. So the frequencies are not random, and so that's what sets our work apart. So we are interested in the case when the frequencies are random, and so the so to make our life a little easier, we start with the two cluster state. And so partly to simplify presentation, so we don't want to complicate our notation very much. So partly there are some things which are easier to study for two clusters, but overall the sort of the approach can be generalized to multi-cluster states. So, another simplifying assumption which we make is since we are interested in two clusters, so we split our group, our network, into two groups. So the first M oscillators. So for the first M oscillators, we assign intrinsic frequencies drawn from the unimodal distribution whose density is shown on the left. So that's this peak around omega-1. So the rest of the oscillators are assigned intrinsic frequencies, which are also random, but they're drawn from the probability distribution with density around omega-2. Okay, so for the entire network, so the density is bimodal. And so that makes it easier for us to analyze these two cluster states. But I just want to say that this bimodality is by no means necessary for generating these two cluster states. And even for analytical purposes, so one can sort of, with more work, one can get rid of this assumption. But at this point, we think this is a reasonable assumption. Right, so, and the last feature of our setting is the connectivity. So in our previous work on the original Kuramoto model, so we developed methods for studying Kuramoto model on various graphs, including random graphs. And so everything that I will talk about so can be applied to these models with non-trivial connectivity. So, but this is not the main focus of our work at this point. And so, but still, to be able to demonstrate that we can handle this, so we want to assign some connectivity, and we use Erdős-Rényi graphs. So where the probability of connections between two nodes is P, and it can be small, it can go to 0, so we can handle sparse graphs. So the only constraint is that P times N should go to infinity, which means that the average degree is unbounded. So that's, so this is our model. So, so our setting is sort of motivated partly by our interest in sort of finding ways for studying stability of clusters. On the other hand, so it's partly due analytical convenience, but I want to mention that the model exactly like this, with exact setting, was used in the context of modeling power grids by so these three authors. Okay, so it's also has some applied interest. Okay, so since we are interested to clusters, so we anticipate two kinds of dynamics, well, two levels of dynamics. So at the one level, so we are, need to capture the macro dynamics of this cluster. So we have two clusters, and to this end, we look at the averaged quantities. So we look at the centers of masses of these clusters, which are denoted by these capital letters, capital U1 and capital U2. And so one should expect that for large N, so this motion, this dynamics, the average dynamics should be deterministic, right? But on the other hand, since we are dealing with the system whose intrinsic frequencies are random, so we also need to account for the fluctuations within these clusters. And so we look at the quantities within each cluster, so the deviations from this average state. And so our assumption is going to be that these fluctuations are, at least to the most part, are small, right? So, so this gives us a certain decomposition into this average dynamics, which we expect to be deterministic, and then the dynamics of fluctuations, which is intrinsically stochastic, and so it requires different analytical approaches. So we start with the group dynamics. As we send n to infinity, and we assume that the size of the first cluster is of order n, so that the relative size of a cluster tends to a certain value chi. So then it's not hard to derive the system of equations for these averaged quantities. So for each cluster, so we have a coupled system of this second order equations with deterministic initial conditions. So the initial conditions for the first cluster, so it's simply the averaged, the mean positions at time 0 and the mean velocities at time 0. And the same for the second cluster, and then they're coupled, right? So to study this system a bit more, so we go to the new variables. And so in particular, so if you take the difference between U2 and U1, so as was noticed in previous works, so this difference satisfies the damped pendulum equation. And so this can be understood by standard tools from nonlinear analysis, phase plane analysis, and a little bit of bifurcation theory. So basically, there are two possible attractors here. So it could be a stable limit cycle or a stable focus. And then in a certain regime, they coexist so that we have bistability, right? And so that's basically the all information which we need from the analysis for the group dynamics. So whenever we have a stable fixed point, so in terms of clusters, it means that we end up with a phased log clusters. So they just keep the same phase difference and the velocity is going to be 0. Whenever we have, so whenever our system settles on the stable limit cycle, so then we are dealing with two clusters which are moving towards each other. And so it's different dynamics, right? Okay, so that's basically all we need to know about the group dynamics. And now we turn to fluctuations. So for fluctuations, so again, so it's not hard to derive the following system of equations. After certain manipulations, so we end up, so let's discuss the one for the first cluster. So on the left-hand side, it looks exactly like the equation for a single oscillator, right? So, okay, here we go. So this quantities Ci, so this is deviation of the intrinsic frequency from the mean value of the frequencies in this cluster. And so it's distributed as G1, and G1 is a unimodal density, which we will assume to be symmetric, so symmetric function, even function. So then the coupling. So the coupling splits into two parts. So the first sum is the coupling in, so for the fluctuations within one cluster. So this is, so the first sum, so these are the fluctuations in the first cluster. And then the second sum, so where we get mixed fluctuations. So where the fluctuations in the first cluster interact with the fluctuations in the second cluster. And so this is multiplied by the coefficient C of t. And this is deterministic quantity, which is determined by the group dynamics. And so here's the precise expression. So it's cosine of the difference, U2 minus U1 plus phase lag. So that captures the structure of this system. So for the second cluster, so we have a system which has exactly the same configuration. And since now we are dealing with this large systems of equations, so it makes sense to take a mean field limit. So when we go to the limit, so we get a system of two Vlasov's equation. So F1 is the density for the first cluster, F2 is the density for the second cluster. So how are they coupled? So they are coupled precisely in the same way as you have seen on the previous slide for the sums. So here is this function C of t, and the integral, which takes into account the sort of interactions of the sort of fluctuations in these different clusters, right? And so at this point, so we have a low-dimensional deterministic system which describes group dynamics. So these are two coupled second-order ODEs. And then at the level of fluctuations, we have two coupled Vlasov's equation. And so this is the system which determines the stability of clusters. So the first condition, to get a stable cluster, we need, first of all, to have a stable group motion, which is either a stable fixed point or a stable limit cycle. On the top of that, so we need, in each of these clusters, we need to have coherence to be stable. And this is determined by the Vlasov's equation. And so in general, analyzing this problem, so it's difficult. So the main difficulty is in dealing with these two coupled Vlasov equation. But still, what I'm going to show you that this system gives us useful insights, even at this level, into the stability of clusters, and it helps us to identify certain interesting scenarios for the loss of stability. And the key idea here is that we can, from our sort of information about group dynamics, so we can identify the regimes when this coefficient C of t is 0 or very close to 0. And then the fluctuations in these two clusters uncouple, and we can deal with them separately. And so this we know how to do. So once they are uncoupled, so you can think of a single population. And like for the original Kuramoto model, so one can identify the region of stability of the incoherent state in this population. So I don't have time to talk about this analysis. So there is a critical value here. And so this is the bifurcation diagram. So this is the order parameter as before, and you can see that at the critical value, so you have a transition to synchrony. So the incoherent state loses stability. So what we are going to do now, so we look at the now our system of two Vlasov's equation. So we can identify a solution which corresponds to the incoherent state, right? And then when this system uncouples, so we can use this information to identify the sort of parameters where the coherence, so where we have this loss of stability for the incoherent state, and in a way, so we get the boundary for the stability for the coherent state. So, well, sounds a little complicated, but so here how it goes. So we have two possible attractors, either equilibrium or the limit cycle. So in case of the equilibrium, we have explicit expressions. And so we can find the value of alpha, this phase lag, which makes this coupling function identically zero, right? And so, so that allows us to uncouple the equations for fluctuations in these clusters. And so after we uncouple them, we can control these fluctuations separately. And we can achieve that the cluster loses stability in a certain way. And so here's an example. So we start with the phased log cluster. So you can see the fluctuations are very coherent in each cluster, right? So, and then since they are uncoupled, so we are going to change the parameters for the distribution of the intrinsic frequency in one cluster, this first cluster, and make it incoherent, while the fluctuations in the second cluster remain coherent. And so this way we achieve the loss of coherence in this two cluster state, where the loss of coherence, right? So this is the diagram which shows us how the order parameter changes in each cluster. So in one cluster, it remains close to 1. So this is for the second one. In the first one, it goes from 1 to values which are closer to 0. And so that illustrates this transition to of the loss of coherence in just one cluster. So this is a similar experiment which we did for the clusters which rely on the limit cycle dynamics. So in this way, in this case, function C of t oscillates. But again, one can find parameter regimes where these oscillations are practically harmonic with average value 0. So using averaging, one can show that again, so in this case too, the fluctuations in both clusters are uncoupled, and one can control these fluctuations separately. And so this way we can find a sort of a mechanism when the cluster state loses stability due to the loss of coherence of the in one cluster, right? Okay, so I'm now I think I'm out of time, so I will just finish with brief conclusions. So first of all, so I want to so I guess the main point of our work is to is this framework for analyzing stability of clusters, which is based on the decomposition into group dynamics and the analysis of fluctuations. And so it leads to, it gives us a system of low-dimensional deterministic system for the group dynamics, and then coupled Vlasov's equation describing the fluctuations. And yeah, and so using this decomposition, so we were able to identify the scenarios of the loss of stability in two cluster states due to the loss of coherence in one cluster. And so I will finish at this point. Well, thank you for your attention.
Lovely, thank you very much, Georgi.
Yes.
Do we have any questions? Well, I will use my host privilege to ask the first one then. When you have these two states, you first assign them the number of nodes to each cluster using the bimodal distribution. And I was wondering how much asymmetry influenced the findings from that, or if it doesn't really play into it at all.
Well, so the symmetry in terms of that the two clusters are equal?
Yeah, so the size of, I think you
no, they don't have to be equal, so that plays no role, yes.
But your extension...
So bimodality makes analysis easier, but in principle, so we think that with some work, so one can do the same even for maybe uniform distribution. So it's more for analytical convenience than okay.
And how would you expect the that analysis to change when you have multiple clusters? Do you think there'll be a limit?
Oh, that's a good question. So the framework, the decomposition doesn't change at all. So this all can be done for multiple clusters. So let's say in general, you have M clusters. So you will end up with a system of M coupled second order equations for group dynamics. And then you will end up with M coupled Vlasov's equation, right? And so on this level, so there's no principal difficulty to extending it to more clusters. But if you now want to get more detailed information, so then even the analysis of group dynamics, so one can handle 3 clusters and still identify stable solutions. But with more, so it just it becomes more difficult to do. I mean, so I guess so the framework I mean works well for more clusters, but getting more detailed information is so it's I mean it's probably so. I mean, we were able to analyze certain 3 cluster states, but when one moves to 4 clusters, so it becomes more difficult.
Yeah, okay. Great, is there any last quick question? Ah. Yes. Joel.
Hi, thanks for the talk. I just have a question about the inertia term. So if you say you have a model of a neuron, what do you think will cause inertia of the phase of an oscillator neuron?
Can you, so I'm not sure exactly what you mean by inertia. So can you just maybe in mathematical terms, so what?
I mean the inertia terms that you have in your Kuramoto model.
So, inertia means second derivative?
Yeah.
And so,
And basically, it means that when you perturb the neuron, the phase doesn't adjust immediately, but it continues to go where it was going to go, but you have to exert a strong perturbation to change its trajectory. And so I was wondering if you have a neural oscillator, what will be the physical process that will underlie this inertia?
Well, so you don't have to view this model as so this model has meaningful interpretation on its own. So I think it should be just viewed as a so we are dealing with the second order oscillator. So you can think of this as a system of coupled pendula, damped pendula, or generators. So if you, right, so it doesn't have to be viewed as a sort of through this, as a generalization of the Kuramoto model for phases. However, there are meaningful applications in this, and I think this inertia term was used to capture some certain adaptation. But this I can't really, so I don't have a good intuition for this, but I know that there was an old paper by Bart Ermintrout, which used this generalization of the Kuramoto model to describe some dynamics in, I believe, in some insect populations or so. Yeah, but you, like I said, so the model is meaningful as is. So it's you can think of this as a system of coupled mechanical oscillators, and so that's how it's interpreted in the context of power grids. Okay.
Okay. Yeah. Thank you.
Sure.